Maxime Fairon. Going to tell us something about supersymmetrical geometry.
Okay, great. So thank you very much to the organizer for the invitation. I'm very happy to be here to honor Sasha's many mathematical lives, let's say. And so what I will be talking about today, it's a mixture of some concepts that we've seen in previous talks. So yesterday afternoon, we have seen a bit of super geometry with the talk of Professor Taktayan. This morning, we had some talk about the geometry of Kalogermosa system by Professor Etikin. Then Martin introduced some deformed Royston operators. And now the starting point for this talk, which is some joint and really ongoing work with my collaborator and colleague Taro Kimura in Dijon. So some things at the end will be sketchy, but I mean, if you have questions and ideas, this will be really interesting to me. But so the starting point is the following. So you may know the Hamiltonian here for the Sutherland system. So we have n particles interacting on a circle, okay? And the fact is that this is related to the root system of an minus 1. So something extremely silly to do and completely uninteresting is to say, well, we can add a copy of an minus 1 to it. Then we just have, two copies of the same system with a different number of particles, but they don't interact. So it's not really interesting at all. But then you have a paper of Sasha and Sergeyev from 2003. It was in 2003 on the archive. We're able to make these two systems interact by using some relation to the root system of the Lie superalgebra an minus 1 and minus 1. Okay, so I think this is something that Martin said that for m is equal to 1, this was already known. I think it's a paper in that case of maybe, well, all the nice people here, so Sasha, Misha, and Oleg in the middle of the 90s. And what I will be interested in later is more the rational version of that. And from what I've seen in that paper, the rational version, in fact, was considered by Yuri Berest and Yakimov, but it's just referenced as a private communication. So I've never seen that paper.
Sorry, the inputs is alpha and beta.
Oh, yes. So just to keep the two kind of systems separated.
The problem is in the additional term. You have
Oh, yes. Thank you. Yes. So this is Y alpha. Yes. Okay. So something is that I wanted to just do a blackboard talk, but then I got scared that I would never do it in 45 minutes. So as you see, these are slides from yesterday evening. This is the first typo. Okay, and so my motivation here is to try to see if there are some, let's say, classical version of that, even though, I mean, there is no nice classical limit to that, as I've been told many times, but still, maybe by tweaking the rule of what we mean by classical, there may be something. Okay, so to be able to get something, let's start just with, in the classical case here, with the rational Kalogermosa system. So how do you construct it geometrically? Well, geometrically, what you need to start with is this space, Cn. So it was considered by Wilson. And what is this space? So it's made of two n times n matrices. Oh, yes, and I should say everything I'm doing is over the complex numbers. Okay, so my dynamics will be complex and so on and so forth. So compared to this morning, when it was said that, okay, you can in some cases not have any singularity in the real case. Here, everything, well, there will be collisions happening, but that's not really important. Okay, so we start with this space, and our space is built of these two n times n matrices, x and y. Then we have a vector w, we have a covector v, and then in that space, okay, we will select a slice. So the slice is just obtained by saying that the commutator of x and y is basically a multiple of the identity plus a rank 1 matrix. Okay, so this rank 1 orbits, it's something that we've heard this morning. And then in that slice, we will look at some orbits. Okay, so here I've denoted that this would be a GID quotient just to be sure, but in fact, I mean, the action on that slice is smooth because I'm taking my parameter here lambda to be non-zero, so it's just a regular orbit space. Okay. Right, so why are we looking at this space specifically? Why is it interesting? Because in fact, this notation is not showing it, but in fact, I'm playing it with a cotangent space there. Okay. I have in fact a cotangent space of GLN plus. Yeah. And so because it's a cotangent space, I have a symplectic form, or for me, because I prefer Poisson brackets, I have a Poisson bracket. And I also have there some action of the group GLN. Okay, because I've told you that I will be taking orbits, but first I need to tell you the action. So on the two n times n matrices, it's by conjugation, and then on the vector you left multiply, on the covector you right multiply. So that's the natural thing to do.
So should it be Cn?
Yes, indeed. Okay, so it's to keep the audience awake that I'm doing any mistakes. Right. Yeah, and it's working. That's good. Yeah. Okay, right. So the thing is that so we have a symplectic form, we have an action, and the two are compatible in the way that I can understand the infinitesimal action of GLN using the Poisson bracket corresponding to the symplectic form and some moment map. Okay. And this moment map, okay, which is valued in the little GLN in the algebra is precisely this part here, this commutator of xy minus w. Okay. And so this is why I can consider this slice and look at orbits in there and have a regular, well, in that case, it's smooth or symplectic modifier. Okay, so I'm telling you that this is the interesting thing to look at, but why? Well, the reason is the following. So generically, okay, I mean, the fact that it's true generically, you have to go to the paper of Wilson, but what you can do is just consider points corresponding to orbits where the X matrix is diagonalizable. Okay. So you will assume that these eigenvalues are pairwise distinct. You would just call them like this Q1, Qn. And then it's a little game, very silly, but that you can do that when X is diagonal, then you can look there, okay, you have a commutator of a diagonal matrix with something else. So on the diagonal, there is nothing. Okay. So in particular, if on the diagonal, there is nothing here, then it means that on the diagonal there should be something because it's equal to a multiple of the identity. So because of that, the W cannot be the zero vector, or at least it cannot be only a zero entry. So in fact, up to still using the remaining GLN action that you have, you can assume that this W is just made up. And when you make this choice of representative, you still have an action of the symmetric group by permuting all the particular diagonal entries. But I mean, it's sufficiently nice that it's finite, so I don't care about it. Okay, anyway, so once you've made this choice of X and W, you go back to your moment map equation. You see still on the diagonal that you can extract the values of this V. And then you ask yourself, well, what's happening with this moment map equation outside the diagonal? Outside the diagonal, it's telling you that this Y matrix, well, has some form like this. So it has some minus lambda or Qi minus Qj appearing. But the diagonal part of Y is completely free. Okay, and it so happens that if in those coordinates Q and P, you compute the Poisson bracket that is induced by the Poisson bracket on this cotangent space that you had by your Hamiltonian reduction, then these Q and P are just canonically conjugate variables. Okay, and so this is really the upshot, because now what's happening is that you can ask yourself, well, what's happening if I'm taking half of the trace of this Y matrix squared? Okay, and you precisely get the classical version of the rational version of what I was showing on my first slide. So this is your rational Cauchy-Hormozos system. Okay. So what is also very nice from this point of view, maybe it's on the next slide if I'm organized, yes, is that you can very easily get an integrable system there. Because what? So I've told you that from my understanding as a cotangent space, okay, if I say that the X is this GLN there, then my Y matrix, it's in the fiber, it's living in the fiber. So I know that any function of the entries of Y, such functions are Poisson commuting because they live in the fiber, okay? So in particular, I know that the trace of the Y matrix to any power, which are invariant functions, so they live on this reduced space, they are Poisson commuting trivially. There is nothing to do there. Okay, and then if you do the counting, basically you can just generically diagonalize Y instead of X to see that these are completely independent functions. And so you get an integrable system. Okay. That's very nice because it looks complicated, but in some way in 5 minutes, you know it. Great. So so my point of view is to try to get a step back from this understanding and try to get generalization from that. Yeah. And yes, maybe a side remark to make the connection with this morning's talk about the Sutherland system. If you want the trigonometric version of that with a sine of this difference squared, you need to play with the product of x and y matrix instead. So this is a small game. Again, you get everything very easy. Okay, so what do I want to say from this point of view? Is that in fact the construction has a quiver underlying it. And this will be very convenient for generalization. So how do I see my quiver? Well, the point is that if I forget at the moment that there is some cotangent space appearing, if I'm considering what is GLN plus CN, well, the point is that in some way, to represent that, I will consider an n-dimensional vector space. And an element in GLN, it's what? It's just an endomorphism of this n-dimensional vector space. That's my x. And then what is a vector? Well, a vector, I can just think that this is something going from a one-dimensional vector space to this Cn. So this is my V with my notation, but here it would be the capital.
Same as 1?
Sorry, and this is a 1.
It's 1.
Yes, yeah, okay. So here it's not a mistake from me, it's just my handwriting. Yeah. Okay, good. So once you've understood that, then the point is to go to the cotangent space. In some way, you need to add opposite directions. That is with quivers, that's how you understand it. So, okay, I mean, the opposite direction to a loop, it's a loop based on the same vertex. So this is why my other matrix is still n times n matrix. And then the corrector here, oh no. Okay, maybe I've swapped V and W, so I may have made a mistake. Anyway, it's not important. The point is that then the V and W are a vector and a corrector. So they should have in some way opposite dimensions. So one is going in one direction, the other in the other direction. Okay. So the upshot is that now, if I kind of understand this big space, my mass surface space before reduction in terms of that quiver, well, I can basically see almost everything, or at least I do. Maybe it requires a bit of training, but hopefully you see it. And the point is that now my integrable system that I was talking to you about after reduction, so this trace of the symmetric function of y, what is it? Well, in terms of the quiver, so basically I can forget about the x, the v, and the w. In terms of the quiver, you can just understand it as going through this loop y a few times. Okay. And some way pictorially, you can encode everything there. And so my point now is, well, motivated by some works that have appeared, for example, in literature, but also really by this deformed Kawajimoto system from the beginning. I would like maybe to build a supersymmetric version of this by just thinking, okay, well, in some way, the upshot is that, well, instead of this quiver, let's put vector spaces, do the same game, and then everything will be working, and I will be presenting something that seems to be completely straightforward, but there are some things that we will need to be careful for. Okay, so did I stop here with those? Yes. Okay, so let's go to Blackboard. Right, so where am I? Okay, so let's start then with just basically trying to explain how to think with quivers, but now in the super version. Yes, also to read it. Quiver, right. I mean, that's the kind of keywords that I want to write, but we will see how I can really achieve this thing.
So sorry, I just wanted to ask. So this was description of Hilbert scheme.
Okay, so the point is that your Hilbert scheme of endpoints in the plane, it has a hypercolor structure, and when I'm describing it like that, I'm making a precise choice. Usually people may be having some stability parameter, and instead of my reduction at my lambda, there you take the reduction at 0, because that's the other hypercolor structure that people work with in general.
But as variety, it's Hilbert scheme, but maybe
as manifolds,
as manifold.
it is, yes, yes. Okay. Right, so maybe I was not really pedagogical, but I've talked about quivers, but maybe people don't know what is a quiver. Hopefully you know, but a quiver is basically just a directed graph. Okay, so for me, a quiver Q will be the data of, well, a set of arrows, okay? So the arrows are going between some vertices, say, so this will be my vertex set. And then I need to tell you where an arrow is starting and ending. So this is why I will have some tail and head map that are basically telling me that if I have an arrow like this, it's starting at T of A for the tail and ending at H of A. Okay, so from there you can just take any finite quiver that you want. Yeah. The only thing that we will do, because we want in the end to have some symplectic or cluster structure, so we will need a cotangent space. So that's this doubling that I've been trying to intuitively explain. So what we will do then is consider the double quiver. Bar, and I will not be writing a formal definition. The only thing that you have to keep in mind is that in this double, I'm just adding an arrow here in the opposite direction. Let's call it A star. So it's the double of the arrow. You add such an arrow for each arrow in the original quiver. Okay, and then what will we be doing? Well, we will be, so if you remember this theory, I was telling you that in some way at vertex here, I was attaching an n-dimensional vector space. Okay, so here what we will be doing is just attach a super vector space. Okay. So I mean, everything is very natural, but we will need to be careful to make sense of what we are doing. So let me just write that we attach a super vector space. Okay, we will call it Vi at the vertex I. And this vector space, I mean, it will be of the form for us C of capital Ni, Mi, meaning that you have an I even elements of basis and Mi odd elements of basis in there. Okay, so far we are mimicking the general story quite well. And then what should we do? Well, in the previous situation, I was telling you that, okay, the arrows should be seen as endomorphism. Okay, so obviously we will need to have endomorphism of the super vector space. This is where we will need to be thinking about a bit. Okay. Okay, so what's happening? Well, let's do this drawing. So we have an arrow A, okay, going from I to J here. And I was telling you what? I was telling you that here I'm putting some superspace of dimension Ni, Mi. Here I'm putting some superspace of dimension Nj, Mj. And so what does it mean? It means that my A will be represented by a matrix, the A. Yeah. It will have some block form as you would expect. And this thing, okay, let me write something that is, well, the notation will be wrong, but I will tell you what's happening. This thing, you should understand it as being a homomorphism from this this VA. So what's the vector space at the starting vertex to VJ, so the super vector space of that dimension at the ending vertex. So here, what I want you to be careful about is that when I'm using this notation, I should be thinking in terms of a functor of points. Okay. So really what will be happening is that in my head, I will be going over all super algebras that exist. And I will in fact be saying that for all super algebras, I will have a homomorphism of Vi tensor the super algebra, tensor Vj tensor the super algebra. Okay. So this is why in a second, I will tell you that there are odd elements in my matrix. But if you just consider that here I have a complex superspace, there is no odd numbers there at the moment. So really, there is the functor of point that allows us to make sense of this. Okay, right. So now what? Well, my B of A matrix is going from this vector space to that one. So let's just be careful about what's happening. So there is in there a part which is going from the even part to the even part. Okay, so this is what I will call BA even, EE. So it's taking here's something of size Ni, giving you something of size Nj. And then you have the same story with the part that is going from the odd part to the odd part. Okay, so we have Ba on odd. It's taking something of size Mi to something of size Mj. And then, as you would expect, you have some terms there of diagonal blocks that are mixing the two parts. Okay, so here, what I call BA, which one is it? Even odd. So taking the odd part here, dimension Mi, to the even part here of dimension Nj. And then similarly here, this BA odd even. Okay. Right, so far it seems that what I'm doing is just making you waste a lot of time because you could have expected this thing. But here you need to be extremely careful because my notation, which is a big abuse of notation, is telling me that this, in fact, is a matrix which is an even matrix. What does it mean? It means that the blocks here that are preserving the parity are made of even variables. Yeah. And then when I'm saying even variable, it's still with this functor point of view in my head that I'm going from something Vi tensor some algebra, super algebra A to Vj tensor super algebra A. So these are even coordinates in this A algebra, super algebra. And then the off-diagonal blocks will be odd. Okay. I mean, the point is that if you know this bitmap, that it's not really, I mean, you know it, so it's not really difficult, but the first time you see it, it can be quite counterintuitive, and you may be losing your mind at some point if you don't see it properly. Okay. Right. So now we have what I will call in some way a super representative space. So let's write it here. So this will be. Okay, maybe it's better. Yeah. Okay, so I will have what I'm writing, the super representation space of, okay, for notation purpose, I will write a parse algebra of the quiver, but just think it will be the representation of the quiver that is there. This will be a super representation in my super vector space V. Okay, so I should have maybe written it here. That I have V, which is the sum of all these VIs that I had introduced of the different dimensions. Okay, and what is this thing? Well, basically, I mean, I want to write as usual that this is just given by all these BA matrices. Okay, write BA star with A in the quiver. Okay, again here, I mean, you need to be careful that this notation it's if you use your functor of points formalism, because I mean these are not points on the underlying variety. You need to be careful about that. Right. So what? Well, this thing, as I was saying you, it's not what you would expect, but in some way it is. Okay, what do I want to say there? Well, remark. So if you know a bit about supergeometry, the point is that you have a topological space, okay, and then you have some sheaf of function on it, and this is a sheaf of superalgebra. So the point is that here the underlying topological space is just kind of the usual one. So the underlying space, what is it? Well, it's just a product of the representation space in the usual sense of the even part, okay? In some way, this means that you in some way consider just all the matrices with the top left blocks. Yep. Times what's happening with the purely so the all diagonal blocks, these are just extra function Grassmann functions that are there, but they are not they don't have any topological meaning. Okay. So here is the thing.
Excuse me, so.
Yes.
But what is V? Because you have so many different vector spaces. Oh, sorry, it's the direct, I missed.
Yes, so, but that's a good question. So my V.
It's the
is
sum of all of
the
these.
super vector
all of-
space.
of all-
And then for V even, for example,
them up into-
yes, so for example, V even is just, I'm taking the C and I zero.
Yeah.
And so on.
Okay, thank you.
Okay, right. And so this is what is happening topologically, but in some way, what I want to do is, for some reason, I want to put a minus sign there. What is the minus space? Well, the reason is that we will want a Poisson structure in the end. Okay, and so here I'm telling you that basically the point is that we will take a super trace. So there is a minus sign that will be appearing. That's what I mean there. Okay, so let's write the first kind of a small result that is easy to derive. So proposition. So this S rep. Okay, so sorry, I will already be, no, I will not be there. Let's write it. It's not so long. Okay, so this space, it has an even symplectic structure. Which is like very easy to write on. Yeah. So my even symplectic structure will be just what? It will be the super trace of something. And okay, if you know the notation for the usual quiver varieties, I will just write it. I will write exactly the same thing, but it's just that the meaning is different. So you will take a sum over all the arrows in the original quiver, and what do you do for each such arrow? You take you make the matrix of the differential of the BA variables. Then you wedge that with the matrix of the DBA star. Okay. Right. So yes, I was saying you there is a minus sign. This is because of the super trace, putting a minus sign on the hot part. Okay. So what is nice with this formula is the following. Because I have a space of matrices acting on some superspace, I can change basis there. So in fact, my change of basis gives me an action of something. So here for each VI, I have an action of the supergroup GLVI. Okay. So here it means that on this GLV, I can take the product of all these GLVI. I get an action of the supergroup GLV. And then it so happens that because we are taking the super trace of something, and my action basically is by conjugation, well, the super trace is invariant to multiplication, so that this thing, this even symplectic structure, is GLV invariant. Okay. So what I'm writing so far, if you know the usual theory in the classical case without Grassmann variables, I mean, if you could write this, it's very elementary. I'm just telling you that you can make sense of all the things in the supercube. Okay.
So, sorry, is it not GLV, but the sum of GLVI, because sum of GLVI is not GLV.
Okay, yes, the notation is not good. Yes, you're right. So let us say that GLV will be by definition the product of the GLVI. But I mean, this is not the GLV, right? Yeah, it just in some way it's a block diagonal part of the big general linear supergroup acting on this vector space. It's respecting the block decomposition. That's okay. Okay, right. What do we want to do next? Well, we have an even symplectic structure. So the point is that we will corresponding even graded Poisson bracket. So you basically just need to invert this one. I will not write this graded Poisson bracket because it's also of the form super trace of some derivative of BA wedge derivative of BA bar. But I mean, because it's super, there are extra signs appearing, and so it's not nice to write it down. But the point is now the following. We have an action of a group, a supergroup, okay, we can consider the infinitesimal action associated with that. And we can ask if it is compatible with this created Poisson bracket, as you would do in the usual sense when you want to then perform Hamiltonian reduction. That's what I have in my mind. Yeah. And so it so happened that for proposition, there exists a moment map for the infinitesimal. Okay, so let me write it, GLV action. So I will not say too much what it means. I mean, if you know the notion of moment map, you just write it and it's the same formula in the super case. There is nothing really important there. The point is then that because of this proposition, you can do the following. So maybe I should tell you what's the form of this moment. So the moment map. Okay. Yes, let's write it like this. So it will be going from GLV. So in some way, this should be seen as the function on the dual of GLV. Okay. So you take the double dual there. You will get functions which are on this super representation space. My notation is the following. And what is it doing? Well, to some element that I will call eta there, you just associate the super trace of something that we know, the commutator of the behavior start with my notation with the eta. So again, if you know the notation in the usual even case, you would know that here there is no super appearing. So this is the nice thing that is happening. Everything is kind of unraveling in the correct working. And in some way, this was the motivation of this work as well, because there is a paper of Taro Kimura, my collaborator, and Vasily Pestun, where they are doing some super instant on counting. And I mean, they are looking at a special case, but in the end, they say, okay, well, you could consider this this sum for any quiver, do some super quiver varieties, but they didn't write anything. So the point here is to also have the corresponding Poisson structure with. Okay, so now is the fact that we can now come to super quiver varieties, which in general will not be varieties, but from this, now we can consider what I will call, okay, let's go there maybe. So we will be able to construct some, let's say at the moment, some super scheme that will be associated with the quiver. Okay, and so how do we construct that? Well, in the usual theory, what you would do is to fix some value, some number to each vertex in your quiver. So you fix what I will call zeta. It's a bunch of zeta I in C to the I. Yeah. And then what you do is that from there, you will create an ideal in this ring of function. We will construct this I zeta, which will basically be obtained by saying that, okay, mu star of, so it will be an ideal generated by going over all the eta in this GLV. And what are you saying? You say that basically when you fix this mu star of eta, it is to some specific value. And what is the specific value? It will be saying that you take the super trace of eta with something that I will write. Okay, let's write it in blocks. So I will have a zeta identity. Okay, zeta 1 identity over v1, and so on and so forth to, let's say, zeta I identity on the last superspace. Yes. And here the eta in GLV. Okay, right. So in some way, what is this saying? If you again, try to understand things topologically. Topologically, you are just basically saying that, okay, the super trace of this thing is equal to the super trace of something else. So in some way, you are still saying that you are cutting out by the same moment map relation as you would have in the usual theory. Okay, so topologically, this is still the same size that is leading to the corresponding quiver variety in the usual sense. It's just that now, because we are in a superalgebra, there are more information.
This is like a stability condition or?
There is no stability condition here. No, this is really the parameter. Okay, it's just that usually people may put the parameters to 0 and work with the stability parameter. I'm doing the opposite.
Okay.
Okay. So anyway, my quiver super scheme, what will it be? It will be the super scheme, whatever it means, corresponding to. So now looking at my big ring of functions, so I have this OS ring. Q bar V. I now quotienting that by this ideal. So it's like imposing my moment map relation, but it's not just, again, a topological relation. There is also something happening on the Grassmann variables. And then you look at the invariant under the supergroup. So again, it's like the usual definition that you would write for quiver varieties, but there are Grassmann variables happening to be there. So what's the relation with the first part of the talk? Well, the relation is the following. So I will put in there. So if you remember, in the first part of the talk, I was saying, okay, you start with a quiver having just one loop X and then one extra variable V, one extra arrow V, then you were doubling it like this. And then you were putting something of dimension N there. Okay. So here in some way, we will put something of dimension NM. Okay. So we are also adding something with odd generators. And then you need to ask yourself, well, what do you put there? And for some reason, I was expecting that, okay, you could put something like 1, 0. But if you do that, then basically, for some reason, you just go back to the classical theory. So it's kind of, I mean, after you do the reduction, it's kind of killing all the odd parts there. So there is nothing really interesting there. So what you need to look at will be this. So you take this super vector space at the starting vertex. We will not make the reduction with respect to it, so it will be like a usual framing for people who knows that. And so it happens that these quivers, in fact, they have appeared in some cases. And so if you take then M is equal to 0 in there, then basically you have some recent work of Arakawa and collaborators who have constructed some super vertex algebras whose
your space V, you know, which is there, it consists of two blocks. One is odd, another even, right?
Yeah,
So-
well, yes.
So then if you do the same, you will never solve equation equal lambda a unity. Because you will have even products in the bivector,
Yes.
but they are not, the square of these elements is 0. They are not ones.
Yeah, okay, yeah, no, but the point is that the unit blocks, they are just on in somewhere on the even parts. Okay. So that's what one should keep in mind. So in some way, yes, the point is that maybe I should develop this. So this thing, what does it mean? It means that you have a zeta 1, then something, let's say N, then you have zeta 1, hit M, and then 0, 0. And the odd variables are there and there. Okay. So here it's just even variables. Yeah. There is no Grassmann variables appearing there.
No, I mean when you build bivector,
Uh-huh.
you have bivector. When you
Yes.
build bivector,
Yes.
then the first block will be a normal, maybe invertible bivector, and the lower block will be even but not invertible. For instance, if you have a Grassmann algebra,
Yes.
right, you have C and you have some theta,
Yes.
and then you have C and theta square,
Mhm.
well, theta bar, whatever. It will be Grassmann, but it's not a unit. You cannot.
Well, okay, maybe it's the point to keep in mind is that we are having this endomorphism. So for me, on the diagonal, I will always have just even variables, even for bivector or anything. The odd part will only be off diagonal. So there is no problem with that. Yeah.
Okay.
But maybe we can discuss that after if I don't understand what you mean. Okay, right. So let's try now to just show you what's happening. Okay, right. So now, so this is what I was telling you. So the small thing to keep in mind, and then I will stop, is that okay. It will be good now. Okay, so the small thing to keep in mind is that, as I was telling you, there is underlying the usual classical theory playing two roles. Okay, so this is why I will have some. Why are you gonna? Hopefully it's better. So here you will have, and well, this will give you in some way the n variables that I was presenting at the beginning of the talk. And then you will have m other variables playing a dual role. Okay, sorry, I don't know why it's. Okay, let's take it off. Let's on again. Okay, let's hope it's work. And then there are some odd variables that are kind of canonically complicated. Okay? So just keep in mind that because we are in the supercase, these things, the Poisson bracket between the two of them is equal to 1, but it's a symmetric Poisson bracket because they are both odd. Okay, and so the point is that you arrive at some matrices like this. So you can still say that generically you can diagonalize the X because this genericity assumption is just something topological. Okay, so you can rely on the previous classical version to know this. And then you ask yourself, what's happening with the rest? Okay, so the fact that W has some ones there and so on, this is something that we knew. But for example, the V vector that we had earlier, it was made of just minus lambda everywhere. Now there are some, this star just means that there are some product of odd variables appearing there. Okay, it is still here's some product which will be even, but there is something. Okay. And then the upshot is to show the following. I've not written explicit expression because, as you saw, I've made many mistakes at the beginning of the talk, so obviously everything would be false. But the point to keep in mind is the following. So if now you compute the super trace of this y squared, okay, so here we need to play with super traces because they are invariant under this GLN action. Okay. Sorry, this GLV action, which is a product of all these blocks. And so you get, as you would expect, well, because of the classical situation, the Hamiltonian for the rational case in 2 copies, okay? And then there are some interaction terms. Okay. So the red part is what I was happy to see because, that's what you would expect from this different Gaussian system that were there before. But the point, and I will finish on that, is that I also have some extra interaction terms here that are made of odd variables, and I don't know, I would like to kill them to have some kind of version of this different Gaussian system, but okay, I don't know if I can really kill them or not. So as I've told you, this is very ongoing for the end, so there are things that need to be understood. Okay, so I will finish by saying happy birthday, Sasha. Thank you, everyone.